Hi students. In this lecture, I am going to discuss problems based on motional EMF and Faraday's law. Let us see first one. See the question given. Figure shows a smooth pair of thick metallic rails connected across a battery of EMF epsilon having negligible internal resistance. A wire AB of length L and resistance R can slide smoothly on the rails. The entire system lies in a horizontal plane and is immersed in a uniform vertical magnetic field B. At an instant t, the wire is given a small velocity v towards the right. You can see diagram here. Velocity given towards right. So find the current in it at this instant. And what is direction of current? Then we have to find the force and show that after some time, wire AB will slide with a constant velocity. And that velocity how much? Okay, this is a question given. Let us see how to solve it. Right, first of all, make the given diagram. So given a battery, so taking a battery here. Now a wire can slide on these rails. So given wire which can slide on that, and this wire is given a velocity v right side, and take this as AB. So given as AB, its EMF is epsilon, right? And field is now normal to this board and outwards. If you take board plane as XY plane, field is now along positive z axis. Now first focus, find the current in it at this instant and what is direction of current. Okay. So we can see here, because of this velocity, area of this loop increases, right? Because of increasing flux, current will be induced, right? Now see, because of that current will be induced means, according to Lenz's law, direction of induced current is in such a way that it opposes the cause of its production. Therefore, because of the induced current, field must be into the board because this field is now outwards. So field is into the board means current must be, it is a clockwise. So this current is clockwise because of induced EMF. Okay. I am not saying net current in this one. Current due to the induced EMF must be, it must be clockwise. That means if you replace this moving wire with a battery, that we have to replace like this. It should be like this. Then because of this induced EMF, current will be like this. Okay. That means now circuit is like this. See carefully. This is the given battery, which is EMF epsilon. This is induced one, that is BLV. This is the EMF induced. Now we can see in this circuit what is net EMF. Okay, that net EMF is equal to epsilon minus BLV. You can see carefully, or you can take same thing by using Kirchhoff's second law, right? Therefore, current equal to net EMF epsilon minus VLV upon resistance R. Okay. Or if you have any confusion, let us do one thing. Write Kirchhoff second law. Okay. Suppose I am taking here. So we have taken current is I like this. This is the net current. Okay. And to avoid confusion, I am erasing this arrow here because direction of current depends on the net EMF. Okay. Now see carefully. If you take now Kirchhoff second law in this loop, I am taking like this -2. That means low potential to high potential. So plus epsilon. Next coming to here, we are moving high potential to low potential. So minus VLV. Next, this circuit is having resistance. See carefully once what is given here. Figure shows it is a wire of length L, resistance R. So we can say this battery is having now some resistance. That means we are replacing this moving wire with a battery of EMF BLV having resistance that is R. Therefore, when we are moving along the current flow, potential difference across this one, it is a minus IR. This is equal to G. So from this we can say I value, right? That is what we got here, right? Next, see what else we have to calculate. So we got now current and direction of current. Since this EMF is dominating when compared to this, net current will be anti-clockwise. That means only, see, if you have only this one, current will be clockwise, but net value, it is now in this way, right? Okay, next focus. What is a force acting on the wire at this instant? Force acting on the wire. Force acting on a current carrying wire. So current is I. That is no. That is no. So F bar is equal to I into L bar cross B bar. And you can see angle between L bar and B bar is 90. It is simply I into L into B. Substitute the value of I here. It is L B upon R. Remaining is now epsilon minus BLB. This is now force acting at that instant. Okay, right. Next, see in that what else we have to calculate? Show that after some time, the wire AB will slide with a constant velocity. Find this velocity. Now you can see this force depends on velocity. And here velocity keep on changes. Let me cross check one direction part. L bar cross B bar. So L bar means direction of L bar is J cap, right? It is J cap. So J cap cross B bar. B bar is now K cap, right? Now see carefully here. L bar, direction of L bar, that is now J cap, and K cap, sorry, B bar is now K cap. So direction of force, it is now along positive x-axis. That means it is now right side. Okay. So now we can see here, as time passes, V value keep on increases, right? It is keep on increasing. At one point of time, this BLV is equal to epsilon. So the question given carefully. What it is given? It shows negligible resistance, a wire AB, right? If you observe carefully, at an instant t, the wire is given small velocity V towards right, small velocity. Okay. Initially, V value small. And here we got a force. It is I into L bar cross B bar, L bar, J cap, B bar, K cap. So J cap cross K cap, I cap. So force is, it is right side. That means speed is now increasing. As speed is increasing, BLV, this value will increase at one point of time. This is equal to epsilon. When these two are equal, force, net force is zero. That means velocity becomes a constant. Therefore, when velocity constant, epsilon is equal to BL, take it as V dash, right? That means V dash value, that constant velocity is equal to epsilon upon BL, right? So I hope you got clarity. Let us go for next problem. Right, see the question given. A semicircular conducting ring of radius r is placed in xy plane as shown. A uniform magnetic field is set up along the x-axis. No EMF will be induced in the ring if conditions given here. Let us see how to verify this. So here semicircular conducting wire, it is moving. That means we are going to use motional EMF. So first let us make the given diagram. It is given X means board plane as XY plane and Z is outwards, means towards us. This is now semicircular wire, right? Condition is that no EMF will be induced in the ring. So one thing we have to understand that since the field is uniform, this semicircular wire we replace with a straight wire. That means we are replacing that with a straight wire whose length equal to diameter of that semicircle. Okay, this is that wire, replacing that with a straight wire. Now you can see that EMF induced equal to L bar dot V bar cross B bar. Okay, next see carefully direction of the field. A uniform magnetic field is set up along x-axis. V bar is along x-axis. It is along x-axis. And we have learned that out of these three vectors, if any two vectors are parallel, E value will be 0. And you can see direction of L bar is along x-axis, right? Along x-axis and B bar along x-axis. Since these two vectors are parallel, irrespective of direction of V bar, E will be 0. That means the options, it moves along x-axis, it moves along y-axis, it moves along z-axis, it remains stationary. Irrespective of velocity direction, this will be 0. That means answer is options are A, B, C, D. I hope you are getting this point, okay? Because L bar along the wire, the length of the wire, B bar along x-axis. Therefore, these two are parallel. That's why this is 0 irrespective of the direction of velocity. Okay. Let us see next one. Let's see the question carefully. A long straight wire is parallel to one edge as shown. If the current in the long wire varies with time as I naught e power minus t by tau, what will be the induced EMF in the loop? We have to find EMF induced in the loop. So again, we have to use now Faraday's law. So we have to focus what is rate of change of a flux. So first of all, make the given diagram. A current carrying wire. Current is now given I, which is depending on which is depending on time. I equal to I naught e power minus t by tau, right? And having here one rectangular loop, it is now one loop, shape is rectangle. So I think we are given here this distance is a d and one side length is a and this is b, right? Okay, let us see how to calculate EMF induced. So first of all, we are taking Faraday's law E equal to minus d5 by dt, right? So first focus, what is a flux through that loop, right? So here you can see at each and every point in the loop, b value not same. Okay, that's why I'm taking here at a distance y from the wire, at a distance y from the wire, taking here one rectangle and this is equal to dy. This is one rectangle. Okay. Now, in this rectangle means in this area, we can take field is uniform because dy is very small. Okay. Therefore, flux in that will be given by area is now b into dy. That is area. See carefully. This is one rectangle. This is b and this is dy area. B value mu naught I by 2 pi y. Okay. Like this, we have to take all rectangles from y equal to d to y equal to d plus a. Okay. So I have to integrate. That gives a flux. Y equal to d to d plus a. Okay. I hope you are getting clarity why we have taken integration. Now calculate this. That flux is equal to, first write down constants outside, mu naught b I upon 2y. Integration of y 1 by y dy, right? That is ln y. Now substitute limits mu naught b I by 2 pi. It is ln d plus a upon d, right? This is a flux through this rectangle, okay, complete one. And we are given this current is as a function of time. Therefore, I am taking here, or let us focus modulus, okay. It is a d5 by dt. It's actually minus here, minus d5 by dt. So here, except I, remaining all are constants. Mu naught b upon 2y. See what is now derivative of 5? Okay, it is I naught by tau, having there minus, okay, because this is a minus t by tau, minus comes here, minus and minus gets cancelled. So mu naught b by 2 pi, I naught by tau, I naught by tau into e power minus t by tau. And remaining is ln d plus a by d. Okay, that is our final answer. Or in the place of I naught e power minus t by tau, I can write it is I value. That means it becomes mu naught b I upon 2 pi tau ln d plus a upon d, right? So this is our final answer. See options. So which option is matching? Mu naught bi by 2 pi tau. This option B is match. Right? Option B is the correct one. Let us see the next problem. A wire AB of length L, mass M, and resistance R slides on a smooth, thick pair of metallic rails joined at the bottom as shown. The plane of the rails makes an angle theta with the horizontal. A vertical magnetic field B exists in the region. If the wire slides on the rails at a constant speed V, show that B equal to. Okay, this is what we have to do. Let us see now how to make calculation. Right, first of all, see the condition given. It slides at a constant velocity. Make a diagram, given diagram. This is making an angle theta, and given field is vertically up and wire slides down with a constant speed, or we can say constant velocity. Right? Now see what we can say. Velocity constant means along the incline, its weight component must be balanced by its weight component is mg sine theta, right? Down the incline. This must be balanced by force due to magnetic field. Okay. Now focus how to get that magnetic force. The first focus because of motion of this wire. Okay. So what is now EMF induced? Because once we know EMF, we can calculate current I equal to E by R. Once we know current, magnetic force is, it is I into B into N. Okay. Let us see carefully. Wire is on inclined plane. B is vertically up. So I am taking here for this inclined plane as XY plane. Let us take this is X down the incline and this is Y. Y is along y-axis. So velocity is now along X direction. Right. Now coming to B, it is vertically up. For B, we can take two components. B is given vertically up. For B, we are taking two components. One is along the incline. See what I can say here. This is normal to incline. This angle is theta because this is vertical and this is normal to incline. This will be B cos theta. And parallel to incline, it is now B sin theta. Right. Now, once again, I'm taking the condition. EMF induced is equal to L bar dot V bar cross B bar. Right. And you can see velocity down the incline along positive x-axis. And this component of field is along negative y-axis. Therefore, between these two, angle is 180. That means because of this component of field, no EMF is induced across this rod. That means now EMF is induced only because of this B cos theta. I hope you are getting this one. I am repeating. We are having B sin theta up the incline. Means along negative x-axis. Velocity is along positive x-axis. Right? That means between B bar and V bar and B bar. Means if I am taking this component, angle is 180. That's why because of this component, There is no EMF induced. It is only because of B cos theta. Therefore, I am writing here L bar along the length, that is y-axis, velocity along x-axis. And this is now again normal to these two, right? Therefore, EMF induced is equal to L into V into, in the place of B, it is B cos theta. Okay. Then current equal to E by R. Then force equal to I into L bar cross B bar. Right. Again here, see which component we are taking. It is B cos theta. Okay. So it becomes now I value. It is L V B cos theta upon R. This is I into L into B cos theta. That is now magnetic force. So I'm taking that here. Mg sin theta. This is balanced by, see what we get there, B square cos square theta. Next L square, B square cos square theta, L square V. See anything else left here? L square V, B square cos square upon R. And here we have to find the value of B. So from this B equal to mgr sin theta, mgr sin theta upon, it is L square cos square theta into V under root, right? Like this, by using motional EMF. First we're finding EMF, then from that what is the current. Once the current is known, finding what is the force acting. If this force is up the incline, like this magnetic force, which has to balance mg sin theta, then velocity will be constant. Okay.